So welcome to another Advanced Higher Chemistry video. We are still in Unit 1 and this video is going to be focusing on electron configuration, and this follows on nicely from the video we just had looking at the rules for filling orbitals. So the electron configuration is the ways in which we can represent where all the electrons within an atom are found. So we're going to be referring to the orbitals in some way. So the two ways we're going to be, you need to be able to write electron configuration are known as spectroscopic notation. Spectroscopic notation is going to be using a list of numbers and letters representing the different types of orbitals. And for each orbital, your 1s, your 2s, your 2p, etc., to the top right of the letter for the orbital, you're going to be putting a number in superscript showing how many electrons are in that orbital. Now, you need to be able to use this notation for the first 36 elements. That's all the way up to krypton. So it does include the transition metals. So you will need to be cautious of when you are filling in the 4s and the 3d orbitals. The second type is more of a diagrammatic representation known as orbital box notation. And what it literally is you have a box for each orbital and you then put the electrons as arrows within those boxes. And because we're using arrows to show the electrons, you're going to need to pay attention to what direction the arrows are pointing to represent the electrons having opposing spins or opposite spins when they're in the same orbital. So first one is spectroscopic notation, and for this it would be good if you had a periodic table in front of you so that you could see and follow along on the periodic table where the element is, so you can see where we're getting these numbers and letters from. So carbon has 6 electrons, it's element number 6, it's in the second period, and it's a p block element. So remember, you're filling all the orbitals in increasing energy. So we're going to have the 1s orbital, the 2s orbital, and the 2p orbital. Now, all the orbitals up until the final orbital are going to be filled. So we're going to have 2 electrons in the 1s orbital, 2 electrons in the 2s orbital, and then we need to think about how many electrons are going to be in that p orbital. If there's a total of 6 electrons, and we're only going to need 2 electrons in the p orbital. Or if you just look at the periodic table, within the p block, carbon is 2 elements in, so that's going to tell you that there's only 2 electrons in the p one. So what we have is 1s2, showing that the 1s orbital is completely filled with 2 electrons. 2s2, showing that this 2s orbital is completely filled with electrons, and then 2p2, showing that the 2p orbital is the last filled set of orbitals, and there are 2 electrons in it. You do not need to leave gaps between numbers and letters at all. You can just do it as a continuous, almost as though it's one word, but you won't get penalized if you leave a gap between each of the orbitals. Now, unfortunately, there are 2 exceptions to this rule, and we will visit these 2 elements when we look at transition metals in more detail, but the 2 exceptions to the normal filling rules come with the elements chromium and copper, both of which are transition metals within the first rule. So they are ones that you do need to know how to write the notation for and get it right. Now, in the previous video, we saw that the 4s and the 3d orbitals are quite close in energy to one another. However, having a completely filled or a half-filled 3d shell is actually more stable, more energetically favorable than having a filled 4s shell. So if you can take 1 electron away from a 4s orbital and put it into a 3d orbital, that's going to create a 3d5 half-filled set of d orbitals, or a 3d10 completed 3d orbital. That's going to be preferential to having a completed 4s orbital and 4 electrons in the the d orbitals, or 9 electrons in the d orbitals. And chromium and copper are the 4th and the 9th elements within the transition metals. So they are the ones where this comes into play. So what we might expect for chromium is that because it is the 4th element in the 3D block, we would expect it to be 1s2, 2s2, 2p6, 3s2, 3p3, 4s2, and 3d4. But remember, 3d5 is more stable. So what we do is we take out one of the 4s electrons and put it in the 3d. So at the end, it ends up being 4s1 and 3d5. With copper, it's a very similar situation. Normally, we would expect it to end in 4s2, 3d9. But again, because of the extra stability of having a filled 3d orbital, we take one electron out of the 4s to create 4s1, 3d10. An extension of noble gas notation, an extension of spectroscopic notation, is noble gas notation. Now, this is just a way of simplifying writing spectroscopic notation. You may see this in old past papers. Do not use it. I'm only including it in the video so that if you do see it written down, it doesn't throw you off. If you're asked to write spectroscopic notation, write the full thing. In noble gas notation, it's a shorthand where instead of writing the full sequence, you're only going to refer to the electrons belonging to the period that the element is in. And then you're saying that all the other electrons can be represented by the noble gas that was at the end of the period before your element. So for example, if we look at potassium, potassium is the first element in period 4. And so the outermost orbital is 4s1. The noble gas before it is argon. So argon would be 1s2, 2s2, 2p6, 3s2, 3p6. So instead of writing that full thing out, we can write argon in square brackets and just include the 4s1. For something like magnesium, which is in the 3rd period, the noble gas before this one is neon, and then we would just add in the orbitals from the 3rd period, 3s2, and so on. Nitrogen, we could shorten it to helium, 2s2, 2p3, but you can see in this instance writing 1s2 or writing helium is about the same amount of effort, so it doesn't matter. These were more common in older past papers, so if you do see them written down, just remember what it means, but you will never have to write noble gas notation at advanced higher. So the second half of this video is going to be looking at box orbital notation. If you want to take a break and then come back, please do. Otherwise, I'm just going to go straight on to the next section. So orbital box notation is a more common way, it's an easier way to visualize what's going on in terms of electrons and where they are. And in this notation, you have to pay attention not just to the Aufbau principle, but also to Hund's rule and the Pauli exclusion principle. Spectroscopic notation really only concerns itself with the Aufbau principle, making sure you get the orbitals in order. In orbital box notation, you've got to show the electrons and deal with where they are in our degenerate orbitals. So when we draw out our boxes, we leave a bigger gap between each type of orbital, and then for degenerate orbitals, like the 2p orbitals, they're all sort of smushed together, so you can tell that they belong as a family. Now the rules. First rule, the Aufbau principle, we're going to fill each orbital in order of increasing energy, which means we'll go 1s, 2s, 2p, then 3s. Second rule is going to be the Pauli exclusion principle, which is when electrons are paired, they must have opposite spins. So that means we're going to have an arrow going upwards and an arrow going downwards. And the third rule, Hund's rule, is that we're going to fill our degenerate orbitals singly before pairing electrons. And this is going to come into play when we look at the p orbitals and the d orbitals. It's not an issue for s orbitals. So we're going to look at the first two rules. So helium has 2 electrons. we must pair electrons to have opposite spins. So see that first one compared to the second one. What we've done is obviously the first one is wrong. It is not filling the orbitals in order of increasing energy. Because we are moving on to the 2s orbital before the 1s orbital is filled. What we must do is, if we've got 2 electrons, they're both going into the 1s orbital, and to show the Pauli exclusion principle, the arrows must point in opposite directions. When it comes to degenerate orbitals, the 3 p orbitals, we must fill them singly before pairing them up. So carbon is a good example here. The 1s and the 2s orbitals need to be filled first, and we need to have the spins be in opposite directions. But then when it comes to filling the p orbitals, we've got 2 electrons to fill. We have 2 options. We could fill them individually, or we could pair them up. Remember that third rule states that you must fill them singly before pairing up. So that top one is the one that is correct. Now, when we look at transition metals, we will be looking specifically at the d orbitals. And when we're looking at the transition metals in the orbital box notation there, we will again come back to the examples of chromium and copper, where we will break the rules so that we can end up with your 4s1 3d5, 4s1 3d10. But apart from those 2 examples, you need to follow the rules for orbital box notation. It is almost guaranteed that you will have an orbital box notation question within your final test. Spectroscopic notation, there is a chance that you will have it, but it is less likely. So this video has looked at the 2 ways of representing electron configuration at advanced higher, remembering the rules for filling orbitals and paying attention to the 2 exceptions, chromium and copper.